stretch. Hooray. All right, so a little bit of housekeeping. You take your cell phones and turn them on mute. If you need to talk, go outside. If you need coffee because you're sleepy, go outside. The exit door is over there. Don't stampede over everybody getting out of the exit in the event of a fire. And with that, we have Deepak here. I'm not going to even try to pronounce his last name. And he's going to talk, what? Deepak, sorry, excuse me. I shouldn't even try his first name. And he's going to talk to us about PayPal's experience with the data lake. So without any further ado, here he goes.
All right. Where's my clicker? All right. Good afternoon, everyone, and thank you for being here. So yeah, a very long name. About me. So I work as a software engineer in Big Data Platform Engineering Group in PayPal. And I have around 13 years of experience in data engineering solutions. 9+ years I've worked with Teradata-based warehouse applications, and around 4 or 5 years recently I've been working in the Hadoop space, big data space. Back in 2016, I was a part of this engineering team that was formed to build foundational big data applications for PayPal's data lake. And we were involved in building Apache Spark-based data ingestion framework, data quality, deduplication framework, and snapshot processes. But as we built these systems or services, we realized that there exists a set of foundational challenges that we have in big data space, and we need to solve those as tools and platform before we can really accelerate our data lake growth. So we formed a big data platform engineering group, and as part of that, we ended up building a complete stack of software and platform, and we recently named it Gimel. So Gimel is, for those who are not aware, it's a Hebrew letter. It means benefactor. And we really believe Gimel will power data lake journey, accelerate the data lake deployment, and all other big data applications. So quickly moving to the agenda. We will be looking at PayPal data lake. Before that, we'll be looking at PayPal at scale, the complexity we have in terms of business and technology, and what data lake really is for PayPal. Data lake is not a product or a project, it's a journey, and it means different for different companies. So to set the perspective, what's data lake for us, we'll be looking at that. And as we did the initial work in 2016, we came across a lot of challenges, and we have categorized them as compute and data challenge. And we'll be looking at the solution we have for the compute, for the data, and putting all these together, the Gimel platform, what it is and how it is going to help the data lake. And finally, we have a few exciting plans. I'll be happy to share that as well. So talking about PayPal at scale, for those who don't follow PayPal very closely, it's one of the largest internet payment companies in the world, and PayPal has grown rapidly. We have acquired many companies, and PayPal includes so many subsidiaries such as Braintree, Venmo, Paydiant, PayPal Credit, Zoom. And talking about numbers, here is our Q3 results from last week. So we have over 3.24 billion in revenue, and we have 218 million active customer accounts who do transactions with PayPal on a daily basis. And just in this last quarter, we had 1.9 billion transactions. Now, I talk about growth. So how fast are we growing? And here is a perspective from previous year. If you look at the number here, we had close to 6 billion payment transactions last year, but just in this quarter, this past quarter, we have 2 billion transactions. That's the speed at which we are growing. So when we look at all these numbers, we see our business scaling, right? So when we see the business scaling, we need to have technology and stack that's really robust and scalable. So I'm just going to give you a picture of the analytical space we have in PayPal. And for those of you who have attended our colleagues' previous sessions, you may be familiar, but it's just a recap. So we have around 15 plus Hadoop clusters, and we are reaching 100 petabytes of data on these clusters. And we have over 60,000 yarn applications that we run on a daily basis on these clusters. And when it comes to compute, we've been traditionally on Hive, Pig, MapReduce, but past few years we've been mature on Spark, and we have use cases running on Beam for a year, and we also have Presto. You may have been in one of our Presto sessions. And we also have a few curious developers who are exploring Flink as we speak. So what is data lake for us? As I said, we have acquired so many companies in the past, and these are all subsidiaries, right? So we have PayPal, Credit, Braintree, Venmo, and because they were a company by themselves in the past, they had their own choice of technology and infrastructure when it came to system of records or analytics. So there is a lot of technology that we have to deal with, and we also have partnership with third parties where we exchange data. Now, the first thing that Data Lake tries to solve is bring all of these information together so that when a user is trying to access the data across Inc., they are only talking about what is PayPal's data or PayPal's credit data or Braintree data. They are not really talking about what is the technology behind PayPal's data. The whole thing is abstracted. The complexity in dealing with these different infrastructure is completely abstracted. So we are just working on a common data layer here where one can access any of these data sets provided they have the privileges and permissions. And with that being said, we actually give the capability to bring everything into a common model. So we not only are looking at what people in PayPal are doing or what people in Braintree are doing, the customers are all combined together and we have enriched information. So we can look at entity level information like I as a person own PayPal account, a Braintree account, I made a Zoom transaction and so on. That is the kind of capability that we want to have as part of the Data Lake initiative. And with that being said, all our core functions that we have in PayPal, like finance, compliance, GOps, risk, or merchant, they will all be much more enabled and capable of implementing all the solutions to drive the business. So in a nutshell, we want to have a single source of information across Zinc. We want PayPal and subsidiaries, all of the information together, and we don't want to talk about the complexities involved in what's the technology to source, what's the technology in the storage, and so on. And really power PayPal and subsidiaries analytical use cases from the data lake. So I mentioned we began building few foundational applications back in 2016. So some of the key features that we wanted to target where we wanted to have configuration-driven applications, which can be figured from metadata. And we wanted to have, we are very heavily invested in Spark. So we wanted to have Apache Spark-based frameworks that does data ingestion, data quality, and operational metrics being collected, and all of them presented in the form of dashboard. And the benefits we really try to gain is scalability in terms of use cases, a better user experience while dealing with data across the Inc., and very fast data ingestion, near real-time data ingestion, so that we can do near real-time analytics. And finally, secure and govern the data. Security is a very important component of everything that we do in PayPal. So we wanted to enforce that in the lake. And we ended up building this back in 2016. So on the top layer, we have the operational system in PayPal. And we had a Kafka cluster where we ingested all the transactional data sets. And we used Spark-based data ingestion streaming applications to produce the data into the lake. And we did event partitioning so that we can have capability to answer questions like, what is my last 30-minute transaction? We don't have to go and write a big process. Just go and look at the event partition on transaction data set. In a similar way, who are my top engaging customers last 30 minutes. We wanted to answer those questions in the lake. And finally, we wanted to make sure the data is certified and it's of good quality, so we had a data quality framework. And all of these were driven through our services. We had a metadata where we managed all the applications, onboarded the data. And we used Parquet. We chose Parquet as our storage format in Hadoop because we wanted capability to answer all kind of analytic questions in all the layer of data. With this being built, we realized that there is a lot of challenges, which is very common, and we had to solve these in a better way to really accelerate our data lake. So we had problems still finding the perfect solution for security, metadata, and data quality. Whatever we had built initially were very trivial rule engine, which could certify the data at count level, but business logic was still a challenge. And because we started the initiative, everybody wanted to onboard the data lake. So we had a huge demand to onboard a ton of use cases on the lake, but we had other problems to solve. We didn't have a good solution for data lineage. If you're running SQL, there are solutions that we have today where there are parsers which can parse the logs, get the SQL and tell you, hey, this application read from this particular table, wrote to this table. But when we're talking about big data space, we have to come to the conclusion that we will have other kind of programmatic applications where it's very hard to find lineage. And even if we did the data movement into Hive and Hadoop, there were downstream systems which were trying to write their own Spark SQL code or any kind of application, and there was no common practice to doing data modeling on Hadoop. And many application developers chose their own format. So again, there is no common practice here. And finally, all of these challenges multiplied manifold when we started looking at integrating data from other subsidiaries, because not the same solution fits for all the kind of companies we have and the data sets we have. So this is, on the left side, we have all these data-related challenges. On the right, we had a bigger challenge in terms of technology. So we always hear new technology that keeps coming up. We were invested in Spark. We had Beam users. Flink came up, and then we have Kylo, which is also a good solution. So if you think about switching one of these technologies, it's a huge initiative for the company. We have to go through a huge learning curve, and it affects our time to market our products, or we acquire talent. That's another cost. And when it comes to the bells and whistles in building an application, every time we build an application, we implement the use case, but then we also go and implement other things like logging, monitoring. If you have issues in the system, how do you get the alerts? So if each of the application teams started building their own logging, monitoring, and alerting solution, we end up spending more time on the bells and whistles rather than the actual use case, which might be just writing a simple SQL to read from one data set, join another data set, and write back to another target. So that was a big challenge, and it's a common problem we faced across all the big data clusters that we had. So I, as a developer, don't worry much about administration, but we have to take into account that once you have a data lake, maybe you have a Hadoop cluster, you're talking about a lot of edge nodes and hosts, and you will inevitably end up having to manage libraries and software on those hosts, so that when you upgrade or when you have any changes in your cluster, you need to manage seamlessly these libraries and softwares so that your end users are not impacted, the applications are not impacted. To give an example, we had an enterprise class 120 node Hadoop cluster in 2016, and we had close to 24 edge nodes. A user would go and log into any of these edge nodes and then start working on the cluster. So if there was any software upgrade, a configuration change, or any other library change, the admins had a nightmare making sure every host is upgraded, every host is in sync, and users are not impacted, and we have an active rolling change. Even if we were to get past all of this, the most important thing is the user experience. That was really terrible. So we think about 3 different kinds of users: as a data engineer or an application developer, then as a data scientist, or a data analyst. Each of them had their own problem when it came to user experience. So we look at this, we have two kinds of challenges, a data-related challenge and a very common technology stack-related challenge. So we wanted to solve all these technology-related challenges in a very generic way so that the use cases and the users and the business can just be focused on the data-related problems. So we categorized all of these challenges into two kinds. We call it the compute challenge and the data challenge. So I want to give you an example of the pain point when you, as a developer or as an analyst, work with Spark application today. So you would probably log on to an edge node, use your hard token, or maybe if you are not having hard token authentication, maybe just use your corp ID. Then you would probably do a Spark submit command, and you would submit a batch application to the edge node. But if you are an interactive user, maybe you will go and start a Hive prompt or a Spark SQL prompt. Now, typically when you do that, Spark is going to talk to the Hadoop cluster, and there will be a yarn application that will be launched, and then there is an interaction between Spark master and the yarn application, and then you get all the results. Now, there is a bunch of problems we have here. If you look from an administrator standpoint, like I mentioned, the edge nodes need to be maintained extensively. Any change to software, they have to be upgraded or updated on all the edge nodes. Otherwise, the jobs are going to fail, or the user is not going to be able to access the cluster. And any upgrade that we do, we have to go through a long cycle because we have to ensure that we have a separate cluster where we go through the upgrade protocol, make sure all the jobs are tested well, and then do a rolling upgrade on the actual clusters. From a developer perspective, if as a data engineer, there is no REST-friendly API. We have to work with one of the command line prompt that offers, and it's not a low latency command line. When you go and do Spark SQL, for example, it's going to go and launch an application, but it has to launch a Spark context, a Hive context, and then talk to the metastore and then get back to you. That takes a minute or two, or even longer, depending on the workload and the queue that you're on. And if you look at how many of you here have experience working with Spark? Can I have a hands on? Okay, not many. So there is an option in Spark which is to cache all of the data that you have in the memory, so that you don't, suppose you're running a set of steps and you are in your 10th step, and you want to resume your job or step or your execution from the 10th step, there is an option to cache. Basically, all the data that you have generated till the 10th step is stored in the Spark application's memory. That's what we call as cache. Now, there are analysts who may want to run a few steps and get the intermediate result, cache it, and they want to share it with somebody else so that the other person need not start over from beginning. Those options are not coming out of the box. And it's a typical use case we have encountered with analysts. They want to be able to share their work, not just the code, but the data as well. And as a developer, most often we have many set of SQLs. If we are SQL developer, we pack them into a single file and then we submit the file for execution. Now, if you are in the 3rd step and you fail, in case of Spark SQL, you have to start over all the way from the beginning. There is no modularity and restartability. These are the challenges we had from developers. And from analysts or scientists, you have to log into a black box, start a prompt, and then work with your code. And there is no way to save the code. You have to copy the code from the command prompt, save it to your notepad. And if you really wanted to share it with your colleague, then there is no way. You have to copy that, put it in a box, or send it in an email. But there are ways today, like we have Jupyter Notebook, where a user can log in and then work with the notebook in a web application, save the notebook and share it with the colleague. But that doesn't work if your Hadoop cluster is Kerberized. And from an operational perspective, everybody had their own way of submitting jobs. And there is no auditing capability that we had, because if you are running SQLs, we have to go and comb all the yarn application logs or Spark application logs to get the statement level execution. But if you're writing a program, we have absolutely no idea what you ran. So we came up with a set of software and tools, and we call it our compute platform. So really this solved most of the problems that we faced in the data lake that I explained just now. First of all, we invested heavily in Livy. So those who are not familiar with Livy is nothing but a REST-based service on Spark. So as a user, you can work with Spark through REST services. You can just give a REST API get or post or put to work with the Spark applications. And you can launch your job from anywhere. That's one of the key features that Livy offers. You don't have to go to the edge node. As long as you have connectivity to the Hadoop cluster, you can just give a post command and then get a result. On top of it, you can execute your steps in a synchronous way or in an asynchronous way. So Livy offers a lot of feature. For that reason, we invested heavily in Livy. In fact, we are contributing back to the Livy code base. We have few bugs and enhancements that we have done. And then with the arrival of Livy, we have integrated sparkling water H2O for all the data scientists. So that solves their user experience challenges. And I mentioned before that we have a lot of hosts. We have to manage software and library. But putting the combination of Livy and the NAS mount together, what we have achieved is the administrators just have to maintain their libraries and software in one place, which is the Livy server. Whereas the APIs that we need for the users to execute, we put them in the NAS mount and we expose the NAS path to all the hosts. That way, either you upgrade Livy or you upgrade the underlying software, you have to do it in just one place, either in the Livy server or in the NAS mount. And we also have other kind of analysts who have been using Zeppelin for working with databases, and we have many users who are working with Jupyter. And again, Jupyter is one area we are heavily invested in. So we have made Jupyter highly available in our system. We have installed multiple instances of Jupyter Hub, and we put load balancer on top of it, so it's highly available. Typically, when you use Jupyter Hub and Jupyter, if you start a session, if the Jupyter Hub is down, it's no longer available for you. You have to wait for it to come back. But in our case, we have put the high availability feature, so all the analysts and all our interactive users, they don't have to worry about that. And there are also other users who are using Squirrel SQL as another web application for their interaction. So we enabled all of these features by integrating them with the Livy server. So this is the new picture of what's going on in our lake or in any other big data cluster that we have. All of these users, whether they are batch, streaming, or interactive, they come and submit jobs to the Livy server, and Livy server does the management by working with the Hadoop cluster. And one other problem that I talked about is the common pattern of logging, monitoring, and alerting, which was lacking before. Everybody wrote a lot of code, spent a lot of time to invent their own way of logging, creating their own monitoring, and then alerting and creating dashboards. So we put Apache Kafka, and we have introduced a new logger. So anybody who runs any application on Livy, we automatically capture all the logs, whether they post it or whether it's a Spark metrics from listeners or whether it is from the Hadoop cluster. All of them are combined together, and they are all indexed in Elasticsearch, and we have created a common set of dashboard. So anybody who is trying to onboard onto the lake to create a new big data application, they only have to worry about creating what their use case is, whether it's a SQL or a small program. They don't have to worry about logging, monitoring, or alerting. And we use Sherlock as an in-house monitoring tool. So we also have a Sherlock logger. Anybody who wants to post a metric for which they have created alerting, that goes into Sherlock. And finally, when we deploy Hadoop at an enterprise level, A lot of things come along with it, and we haven't changed any of those. It's just to highlight that we still have the Ambari, Grafana, Dr. Elephant Eagle, SmartSense, and History Server. They're all running as is. So these are the new features that we have added as part of the compute. So just to recap, we had problems from administrators that we were able to solve with this architecture, and then developers had a better experience. Same thing with analysts and scientists. And finally, we were able to achieve something really cool when it came to alerting, logging, and monitoring. And with that feature, we are also now able to capture and audit every statement that somebody executes. Even if you wrote a Scala program, which is 500 lines of code, we know what each line is, what it did, and what was the execution time, and so on. And all of those are completely available in our Kibana dashboard. If one runs an application, maybe in a couple of minutes, you will be seeing the entire information in Kibana. So that's one side of the story. Now, even after solving all of these for our applications, as a developer, we may work with various storages. When we talk about data lake, it's not just a single store. It's a lot of different kinds of storages like HBase, Hive, maybe Kafka, maybe Elasticsearch. You may have data in Aerospike and so on. It's really a combination of various storages. So if you were to work with HBase, today this is the state. You need to write this piece of Java or Scala code to be able to work with HBase. Or you may have to use Apache Phoenix if you want to write a SQL, but you cannot combine data or do any processing on top of it. Similarly, if you want to work with Elasticsearch, you have to write a code like this. Basically, you need to learn a programming language, and you need to learn Spark or Flink or whatever you're going to run on. So putting that into a bigger perspective, we have HBase, we have Aerospike in PayPal, we have Elasticsearch, we have Druid. So if I go and tell my analyst or user, hey, write this code and then you can work with data lake, you're good, he would not be happy. And if I want to expand that to a bigger picture, this is the complexity we have in the industry as of today. If you can see, these are all the different storages at the bottom, and these are all the compute options one has, and you have an infinite option to pick and choose and code. So if you are a development team or an engineering team trying to access and work with the data across all these storages, you onboard your application one time. Maybe you said, okay, let me learn, let me do it. Then you would probably do learn, code, optimize, build, deploy, and run. But if your compute engine changed, for some reason your organization now decided, I don't want to be on Spark, I want to be on Flink, then you have to go through the entire process. Similarly, if your compute version changed, for example, we in PayPal were on Spark 1.6 sometime back, we upgraded to 2.1 and 2.2, and a lot of people had to rewrite code. The code did not run as is. So you do the entire cycle. Similarly, if the API changed, we have something called a create RDD, and then it becomes a create new RDD, the code breaks. Storage connector changed, same issue. Storage host migrated, same issue. If your storage changed, this is a very typical pattern. We chose HBase as our storage for one of our use cases. After we ran on production for a couple of months, we quickly realized HBase is not what we should have chosen. We wanted to migrate to Aerospike, but then all the code changed. So we had to go over this cycle. So this is a typical cycle we have, regardless of any of these problems that we go through, right? So we wanted to solve this in first hand before we go full blown into data lake and say everything is good. So we came up with a data platform or a data API. So this is what we have today. We have introduced two components here. We have a central catalog and then a unified data API. So the central catalog is where the users will onboard new data sets. Basically, if I have a data in Kafka, let's say I have a Kafka cluster, I have a Kafka topic, Then I go and onboard my Kafka topic in the catalog. I give the specs of the Kafka topology. Say, this is my Kafka broker, this is my Kafka topic, and this is my logical name. I'm going to specify a logical name, my Kafka table. And once I have that, I can go to my data API and query that using a single unified API or a query. So really the objective that we are trying to achieve with data API is we want one single API, regardless of whether the compute changes, regardless of whether the storage changes, and we want our interactive users to be more happier. So we want to introduce SQL on top of any storage, and we want that to be capable of running on any compute, not just Spark, which we are invested in. And from a data catalog perspective, we want everybody to go to the catalog, explore all the data sets in one place, onboard data set in one place, and manage them in one place. So this is the problem we were looking at before. With the arrival of data API, this is the state today. Regardless of whether the data is in HBase or Elasticsearch, Aerospike, Druid, or Hive, HDFS, the user is always writing only one line of code, dataset.read or dataset.write. If it's a streaming job, it's either datastream.read or datastream.write. And these are logical names that we have in our catalog. With the logical name, we do all the hard work by generating the code for those storages and then executing them on Spark. Still, we have one more problem in hand. We have a lot of SQL savvy users and they are not happy with this. They want just a SQL to run, right? So we enabled SQL on top of all these storages. So from now on, you can do select star from any of these as long as you're working on Spark Compute Engine. So to give you a little more perspective on what this achieves, suppose you have a use case, you want to run data on Kafka, you want to consume some data from Kafka, push it to Hive, partition it. It's a typical use case. So this is a code I have from my production cluster. Basically, we are reading from Kafka. We are pushing to HDFS. We are partitioning by some timestamp. And with this single code, we are able to achieve the entire use case. So user has packed this code into a file and then submitted to Livy. Behind the scene, we go to the catalog, figure out what is this data set, where it is coming from, what is the code I should generate, and how I should execute it. And to take it to the next level, a lot of us who work with program, we like to use options. In the sense, I want to pass parameters so I can configure my job, tune my job. Now, those features were missing initially when we enabled SQL, and that's something we wanted to make sure we are making available. Typically, if you're working with Hive SQL or Spark SQL, you might be using some of these set options. You do set key and value. Those are transformed to key value pairs and parameters in Hive context. So we enable the same feature here. As you can see here, if you're working with Kafka, if you're familiar, it might make sense. You might have to checkpoint your offsets every time you read from Kafka, because Kafka is a buffer, and then you read 10 messages. The next time you go and read messages from Kafka, you want to read from 11th message. Now, how do I checkpoint? Because the user is now running just a SQL. What is the option for the user to specify where to checkpoint and how much data to read from Kafka? So those options, we have made them available through our set options. So as a developer, if you are thinking, I want to consume from one Kafka table, partition in some data into HDFS, and I want to run in a batch mode, and I want to set some parameters, this is the way to do it today. And how are we achieving this? So we have introduced a new feature in Livy, which we call as Spark Magic. So by putting this particular magic word, what happens is every time you submit a statement to Livy, the Livy is going to first interpret this statement. And as soon as it finds that we are talking about Gimel magic, it's not going to push this query to Hive, which will fail because it does not know how to read Kafka. So it's going to call our data API library, which is going to generate a code. So that code will be generated, and then the whole code will be pushed to Spark. That's how we are transforming the SQL into a particular Spark application. Now you might be wondering, you're working with Kafka. Mostly people stream from Kafka. So we enable that as well. So if you want to stream from Kafka into HBase, you don't want to stream to HDFS. That's a bad idea. Maybe you want to stream to HBase, then that's available too. So we do insert into HBase. We are not partitioning. It doesn't make sense, but we are reading from Kafka. And when you're working with streaming, you talk about streaming window. I want to do streaming window of 5 seconds, 3 seconds, 10 seconds, and so on. So those kind of options are also enabled here. So I'm just presenting here a couple of examples to showcase HBase and HDFS ingestion from Kafka. But we have enabled different properties that are specific to Elasticsearch, Aerospike, HBase, and so on. So with this arrival, you write your application once, which is nothing but a SQL, and then whether the storage changes or compute changes or API changes, regardless of what changes, our data lake users don't have to make any change. With that, the users are able to really focus on the use cases or not worry about any of these big data technology challenges that we have. Quick time check. Okay. So putting all of these together, I have talked about so many different challenges in the solution, but what's the bigger picture here? So this is our Gimel platform. At the bottom, we have our data platform, which is basically a unified API or a SQL API through which you can submit all of your logic as a SQL. Today, we are supporting Spark because PayPal is heavy on Spark, but we have plans to support another compute engine whenever time permits. And from a user experience perspective, we have the compute platform, which solves all these logging, monitoring, alerting, and other stuff, and also gives a very good experience for users, whether they are data scientists or whether they are interactive users like analysts or whether they are application developers. So that's really our Gimel platform. And with this, we really believe we want to be able to power our data lake initiative, accelerate it, and even other big data applications that we have today. So one last thing before I conclude. Like I said, in 2017, we began this initiative. We did a POC, we proved that it works, and we got our blessings from management. And we also enabled these different storages. So we have a Teradata connector, we have HDFS connector, we have a HBase connector, that is a Hive connector. We have Elasticsearch, Kafka, Aerospike, and Sherlock. And we also have, on the compute side, we support Spark, Hive, and Presto. What this means is we have wrappers where you have a SQL and you can just say execute SQL, a SQL file, and you can choose -C. C is nothing but a compute maybe. You can say Presto or Presto or Hive or Spark. So once you issue one of your choices, we basically choose the engine that we want to execute the SQL. And 2018, we plan to add support to Druid and Cassandra because these are a couple of our production clusters. We want to be able to support everything that PayPal has in the first place. And one important thing that I want to call out is the web UI and catalog. We are also investing. One thing we believe is the experience is not great until you have a UI. We need a UI to give a good experience to everybody, a seamless experience to everybody. So we are creating a UI where we can manage all the data sets, onboard data sets, and be able to scan and register data sets. You as a user will just log into the UI, register your application, go to another UI, Jupyter, and then query. We don't want anybody to have an experience where they are required to log into a black box. And this is the part that's really exciting to me. We are planning to open source all of the data API connectors that we have early of 2018, and we have already started thinking along those lines. We have started organizing our code base in a way we can be ready by early next year. And for the future, we have a few other plans, but this is all, we will go there as we get there. Yeah. All right. I will open up for questions. Thank you.
Paul Underwood from Barclays here. I was just wondering, on your data lake, possibly your analytics platform, how many users have you got on the platform, and have you had any issues with performance, or was there a kind of a top limit of users that you wanted to have on that analytics platform? Sorry, on the data lake.
Sure. I will answer this in two points. First thing is, within the actual data lake that we have, we are still working on onboarding users because we want to secure the data in the first place. We have been able to ingest data, bring data from various subsidiaries, but security is, like I said, is the top priority for PayPal. And without having the right security and checks and balances in place, we are not comfortable exposing the data to users. But we have applications which run on this data and then move the data out to either Teradata or other places. So that is happening. So we have batch applications which are running on top of the data lake. Interactive users, we are not there yet because of security reasons. And in general, there are other Hadoop clusters where we have a lot of users. I can say in the order of hundreds when it comes to analytics users who are all accessing our Compute API. Compute API has been there for almost 1.5 years now. So everybody, a lot of people use Jupyter to log in because we added, one of the things I want to mention is we added Kerberos integration into Jupyter, which was missing, and we committed back. So our clusters are all Kerberized. So with that feature, people are able to log into Jupyter and they are able to work with our cluster and the data.
Hey, Deepak, quick question. So in the compute solution that you showed, you have Livy that's outside the Hadoop cluster, and you just spoke about Kerberization. So once you take all that, the request that's coming in through Livy, how do you manage security around it? That's one. And second part I wanted to see is how do you handle the problem where you said, when someone has to share a piece of code or piece of work that they have done with others, you are facing a challenge with that. How do you take care of that? Thank you.
So let me give the first answer from a Jupyter perspective. So if you're logging into Jupyter today, you would probably open a web application and then start querying something or writing some code. But because we have our system Kerberized, we need to have we have two-factor authentication. First is we log in with our LDAP user ID. So once we are in the LDAP account, and then we need to have a key tab to work with the Kerberized cluster. So we open a terminal and then we do the K-init. The user has to do that. That's one black box the user has to go through as long as Kerberos is there. Once the key tab is generated, once we have a token from the K-init command, then we are able to work with the Hadoop cluster. And second question, I missed it, sorry.
You said about developers having challenge to share a piece of code, they have to copy it, put it in Notepad, and then share it. How do you take care of that?
Yeah, in Jupyter we have a feature to save our notebooks and share it with others. In case of our Compute API, what we are doing is, maybe I can go back to the slide. Yeah, so if you look at this particular area here, when the notebooks are saved in Jupyter, we actually have enabled something called NAS behind the scene in Jupyter, and we are going to migrate that to a distributed database. So when you save all of your steps, execute your steps, we are going to save all of those steps in the database, and when you resume, those steps will be resumed automatically. But when you save your notebook, we also have, that's one thing we are doing in a crude way today. We save the notebooks and you have to share the notebook link to somebody else. And maybe you can create a template and share it with others. But it has to be saved in the NAS mount. But we have plans to move away from that particular pattern and move it into a GitHub pattern, where you can save your code and we push it into GitHub. You share your GitHub link to somebody else. That
will ease your deployment option.
Yes. So that's one of the things we are planning to add very soon.
You mentioned as one of your challenges over in the corner down on the bottom, data models. And I didn't wanted some clarification on what you meant by that and how you addressed that. And
Yeah, sure. So we have not addressed the data model problem as such. Actually, what we wanted to address was the technology side first, because once we take care of these technological problems, then we thought all the data problems can be dealt in a different way, use case by use case basis, because there is no one single solution for all the use cases, right? You can model your data on Parquet, but the same thing may not work for some other use case. When you ingest data, you don't want to ingest as Parquet. So for that purpose, we wanted it to be more use case driven, not technology driven.
Yeah, I see all the products up there. How do you manage and maintain and administer all the products? What do you do to keep track of all of it, and how do you apply to those patches and everything in a reasonable time?
Sure. So let me go over some of them. We have the Livy. So what we have done is we have forked our own Livy, basically. We wanted to contribute a lot of features back to the Livy community, but there were discussions and we thought it's better to leave it outside Livy community because of the charter that Livy has. For example, through Livy open source, you can run Spark jobs, but in PayPal, you can run Hive jobs as well. We have added some features. So what we are doing is we have our own DevOps cycle where we go through the build, deploy, CDCI cycle, if you know what I mean. So we have all the code base in GitHub. If you want to add a feature, we go and give a code review and then go through a code review, commit cycle, and then we have a CI/CD cycle. And then once we deploy onto one of our Docker images, if everything works fine, then we deploy the same into one of our production clusters. But it's a rolling upgrade because we have enabled high availability for Livy server. In the sense there is a bunch of Livy servers and we have NAS on top of it and high availability. So you can deploy on one without impacting any user application. That's what we do when it comes to Livy. And Jupyter Notebook works in a very similar fashion because we have added few features and we keep adding features to Jupyter Hub. We have high availability, so when we build, when we do CI/CD, and then when we deploy one host after another. So if any problem arises, it's probably local to the host and we don't have any issues in terms of users availability. And the data API which we are planning to open source, that is a library. So it is not an infrastructure. You can just build the library or download the library and then add it to your Spark job and then work with it. So there it's a simple cycle of just build, do the coding and then build. Does that answer your question? Okay. Thanks.
Yeah. From your session description, PayPal also has here. Yeah, PayPal also has multiple Teradata installations. So how does Teradata UDA or Teradata participate in your big data or data lake strategy? I mean.
Sure. So our Teradata team is here. So we are talking about two things here. One is technology solution. One is data lake strategy. So we partner with Teradata team very closely from a technology perspective. For example, when we added the Teradata connector, we work with the Teradata team to make sure we are doing the right thing because this is completely new. We are working from a Spark compute engine and we are trying to push data to Teradata, reading from various places. We wanted to make sure we are not doing something that's terribly wrong when it comes from a Teradata angle. For example, when we initially coded, if you are familiar with Spark, Spark has this concept of executors cores, which is nothing but it provides a Java process with multi-threading and so on. But that doesn't work well with Teradata. So we had to closely work with the Teradata team, understand what we should be doing in the right way so that we implement the right solution when the connector is deployed for Teradata.
We're also planning to heavily use the query grid going forward.
Yeah, good question. So as you can see, we are ambitious but limited resource. So we are a 10-member team right now, including me, and there is one lead along with us. So we one of the things that we have taken in terms of the path forward is we call the inner source. So as we see other teams are working and they have more expertise, for example, Druid, there's a team who has been on Druid for a long time and we are relatively new. We are asking them to contribute the connector. On similar fashion, if there is another team who is much more sophisticated in terms of working with Cassandra, we would probably work with them to add the connector. That way we can mentor the developer who is actually contributing, and it's a two-way win for both of us. But really the way forward for us is once we open source, we see a lot of people who can contribute from the external community. That's the way we want to expand from a data API perspective.
Any other questions? Any other questions from the virtual session? No? All right, well, thank you for your time. Thank you for Deepak. It was awesome. Please don't forget to rate the session.